Good morning, everyone. Thank you for calling to this webinar. My name is Julio Zimbron. I am with E-Flux. And today we're going to be talking about natural source on depletion, which is a term that is used to describe the biodegradation of petroleum in the ground. I have that it's about 4 minutes after the hour, so we might want to stay here just for 1 more minute to allow other people to dial in. Meanwhile, if you have trouble listening to this, you can send me an email. I will send you a chat to everyone to remind you that you have the option to communicate with me by chat. So I just send a message by chat reminding you that you have the option to communicate by this means. If you have any trouble with the audio, you might want to dial in by clicking on the audio option. And you also, when you have questions throughout this talk, you can ask them by these means, and they will be answered at the end of the talk. So it's now 6 minutes past the hour, so we're going to get started. Again, my name is Julio Zimbron, and I will be talking about natural source on depletion, which is the term used for biodegradation in the soil. Before we get started, I'm going to do a bit of an introduction for myself. I now work for E-Flux. I have my professional background is chemical engineer. I have a PhD in chemical engineering from Colorado State University, and I have worked as a research engineer for different large companies. I also have been an environmental consultant right after grad school. And I have always worked as an applied researcher. My last job, my previous job to this one, was at Colorado State University as a researcher, where I developed one of the available techniques to measure natural source on depletion in soils. So once again, thank you for the opportunity to present this webinar to you. And let's get started here. The subject that we will be talking about is the biodegradation of petroleum in the ground. So this particular slide shows that typically the oil spill occurs near the ground, and then it sinks through the unsaturated zone, also called the vadose zone. And when it finds the water table, the vertical spreading stops and the lateral spreading starts. And here the petroleum interacts with both groundwater, part of it dissolves, but it also interacts with the vadose zone. And what has been shown is that when biodegradation occurs under anaerobic conditions, you have the production of carbon dioxide and methane. This reaction is called methanogenesis. This particular picture right here shows a core of soil from a contaminated site, and this shows that the soils have been stained black, and the reason is that the Sulfate has been used as an electron acceptor to biodegrade petroleum and has turned into sulfide. We also have a lot of bubbles here, and these bubbles are composed of biogas. The biogas is essentially the CO2 and methane. So both of these gases are relatively mobile in the vadose zone, and when they are generated, they move away from the source. And that means upwards. When the methane encounters ambient oxygen at shallow depths, itself can be used as a carbon source by the microbes and generate CO2. So in the end, the CO2 produced here in this methanogenesis reaction and through the biodegradation of methane by in the presence of oxygen, all of it, it shows up at the ground surface as carbon dioxide or CO2. And of course, you can measure the production of CO2 like that, but you also have natural production of CO2 by natural processes in the ground as part of the carbon cycle. So the key here is if you can differentiate between this carbon dioxide that is produced by natural processes from the one that is produced from the biodegradation of petroleum, then you can determine how fast these processes happen. So the materials that I will cover today are, I have developed them as a researcher and have been shown as part of the ITRC LNAPL class. If you look for this online, you will see some of these materials. I also have given multiple conferences in the US to regulators through the TANKS conference in 2015 and the ASWAMO meeting in 2016. And what happens is that natural source and depletion is gaining prominence here, and now is being included in some public documents, including there's the API, the American Petroleum Institute, just released a guidance document on methodologies for measuring natural source and depletion. There's also an update to the ITRC LNAPL guidance document that will include natural source and depletion. And in Australia, they are developing a new guidance document on these same processes. And what you will find in this talk is consistent with all of these documents. So in this talk, we're going to mostly focus on what happens to the petroleum when it biodegrades in the ground. And then how to measure these processes, the different alternatives. So the idea is that you can integrate these concepts into site management. You can use these concepts to figure out what is happening at the site, what site consultants call the conceptual site model. And this should help you make important decisions at your site regarding natural source and depletion. You can estimate the efficiency of other remedial alternatives and when to switch from one remedial alternative to another one in the life cycle of the project. So first, a little bit of chemistry here. There's this concept that the degradation of petroleum is an oxidation reaction. So it generates electrons. And for this reaction to happen, you need a corresponding reduction reaction. And these reactions are accept electrons. So when you have two things, then the biodegradation of petroleum can proceed. So this leads to the concept of the electron acceptor ladder. So which electron acceptors are used depend on the energy that they release, and they are ranked here by energy. And microbes actually switch sequentially from these different electron acceptors. If there's oxygen available, the aerobic microbes will degrade the petroleum, but oxygen has limited availability in the ground, so the media runs out of it, and at that point the microbes will switch to alternative electron acceptors, being nitrate, manganese and iron oxides, sulfate. And ultimately, if all of these are depleted, then microbes revert to this reaction of methanogenesis. And methanogenesis does not require external electron acceptors, and it produces CO2 and methane. So when you look at the conceptual side model for an oil spill, the main reactions are either methanogenesis here at depth, and the reason is that the external electron acceptors have been depleted. And here, where the methane encounters the oxygen, you have the top of the electron acceptor ladder, which is the availability of oxygen for these reactions. You could have some of these processes happening in between if you have some of these electron acceptors still available, but typically they are depleted. Some of these have an inflow with the groundwater, and there's some small amount of biodegradation occurring through these intermediate reactions. So the ITRC is a guidance document that is commonly used in the US and throughout the world to conceptualize your petroleum spill. And the ITRC provides a background to make an estimate of these biodegradation reactions. When you account for the flux, the mass flux of electron acceptors in groundwater, you can estimate the associated mass that is biodegraded of petroleum due to this utilization of external electron acceptors that are coming in the groundwater. So this is a bit of a horizontal mass balance based in groundwater parameters. However, you can also do a mass balance based on the vadose zone due to gas transport that occurs vertically. And this is based on the mass balances and fluxes of these gas species. So this slide, so the quantification of fluxes relies on this concept that you draw a control volume, a control surface around the area that you're trying to study, and then measure the fluxes either of dissolved species in groundwater or gas fluxes in the vadose zone. And this is really a very powerful tool. These control surfaces are really arbitrarily defined, and you can define them somewhere in the vadose zone for gases, or you can also define them at the surface. And of course, for groundwater, you define them based on monitoring wells. So what are the natural source and depletion monitoring alternatives in the vadose zone? And in this talk, we mostly are going to focus on the vadose zone because, as will be shown later, that offers the highest mass depletion rates estimates. People have spent a lot of time measuring those based on groundwater parameters, but the experience shows that that only accounts for a small fraction of the biodegradation rates. So a lot of the action happens in the vadose zone, at least in terms of what is measurable. And the reason is that these sources are typically methanogenic, and both methane and CO2 show up in the vadose zone. So based on that, the monitoring alternatives are first the gradient method. And the gradient method assumes that diffusion is the main mechanism for biodegradation, and you estimate these diffusion-based fluxes by measuring the concentrations of gas species in the vadose zone and then feeding that to the diffusion equation, which is also known as Fick's equation. The alternative, if you define your control plane at the ground surface, you can measure the degradation rates by measuring the soil gas flux of CO2 that is coming out of the ground. And there's two alternatives for doing this. The first one is called the chamber method. And the chamber method, you essentially put a closed chamber or a bucket essentially on top of the ground. And initially the CO2 concentrations there are ambient, but as it's getting a flux from the soil, those concentrations raise. And you can use the change in concentration to fit to a mass balance to figure out the flux. This measurement is for a short term. The second alternative to measure soil gas fluxes at the ground surface is based on this technology that was developed at Colorado State University and that is now commercialized by E-Flux. And the idea is that if you capture the CO2 as it's coming out of the ground, for the length of the measurement, the mass captured is associated with the average long-term flux of CO2. So in the next few slides, I'm going to be describing the details of all of these three techniques. The gradient method, as I indicated, right here we have the concentration profiles of different species, which are methane, oxygen, and CO2, and how they change with elevation. So this is a relatively deep site. This is a paper from the group of Paul Johnson that is now, almost 2 decades ago, old. And what this shows is how the methane is being produced at depth as well as CO2. And as both raise into the ground, the methane depletes the oxygen. And the idea here is that this is the fixed law of diffusion. J is the mass flux of the species of interest, and that is proportional to the change in concentration with elevation times the in situ diffusion coefficient. Of course, measuring concentrations is relatively easy. You need a sampling port and a meter, but the tricky part here is estimating the in situ diffusion coefficient, and I'm going to elaborate on that in the next slide. But there's a fair amount of uncertainty associated with that. So this equation requires that the gases don't react when you're measuring this change in concentration. So you need to use essentially the flat portion of this curve to estimate the diffusive flux. This is the method originally included in the ITRC guidance document. And the biggest advantage of it is that it can indicate where specific soil processes are happening. So if you see a portion of these curves that is not flat, it's probably because these reactions are occurring, so these species are being produced or depleted, and that goes against the assumptions of this diffusive flux only. You can also have some issues because the soil is not homogeneous, so this in situ diffusion coefficient changes throughout the soil column. And this is how the gradient method is implemented in practice. You essentially install a well, and around that well you install sampling ports. There's some tubing that connects different portions of the soil with a sampling port at the surface. This is the finish at the ground level. In this particular case, we use some of these sampling ports to connect to closed vials where we put pressure sensors to estimate if there were some barometric effects throughout the soil. And ultimately, you put all of these sampling ports, and in this case, the bottles, inside a finish at grade. This is how the implementation of the measurement of the in situ diffusion coefficient occurs. You have a sampling port like the one that I showed in one of the previous slides, and you essentially do what is known as a push-pull test. You inject a known volume of gas into the ground. The gas has a tracer, and then you retrieve that slowly at a constant rate by using a pump. And when you retrieve that, the concentration, the plot of concentration versus time will indicate how this volume of gas interacts with the soil, and you ultimately can extract the in situ diffusion coefficient from that. This is another paper from Paul Johnson from '96, and the problem with this is that this estimation of in situ diffusion coefficient is only specific to the time and the location where the test was conducted. So this in situ diffusion coefficient can change quickly with changes in soil moisture. So these have to be measured at the same time that the concentrations in the ground are collected. So some of the limitations of the gradient method are that it's labor intensive. It requires some amount of post-processing. You also require a fair amount of field work and installation costs. You need the soil transfer properties at the same time as the concentration profiles. It assumes that diffusion is the only mechanism for transport. So you have to be careful when you have reactions occurring, or when you have changing conditions, or when you have advection effects, when you have pressure differences in the soil. That can cause advection that is not accounted for by this method. The second method that I will show here is called the dynamic flux chamber. And the dynamic flux chamber, as I indicated before, it's essentially a bucket that you put on top of the soil. This is essentially a fancy one, off-the-shelf commercial equipment that is connected to a soil meter here in the yellow box. So the concentrations inside the chamber change, and you measure those with this online pressure concentration sensor. The concentrations changing in the soil can change the soil fluxes. As the concentrations increase, the soil fluxes are reduced, so it then interferes with the process it tries to measure, and that's why these chambers are only deployed for a few minutes at a time. If you want the long-term average, you need to conduct multiple deployments during at multiple times. One limitation is that you only know how much CO2 is coming out of the ground, but you don't know anything about the source. And as I will explain later, you can use some carbon isotopic techniques to determine that. But this technique is not carbon isotopic friendly. In my opinion, this is probably best suited as a screening tool to map the sources. It can be used for any soil gas, but it's mostly used for CO2 because you need a real-time sensor for other gases. It does include diffusion and advection. And here there's a plot of 9 different locations in which this technique was applied at different times of the day for a period of 24 hours. And what this illustrates is that these soil gas fluxes vary like a sine wave. You have a maximum and a minimum during a 24-hour period, and the reason is that ambient pressures change. So when you have a high pressure occurring in the ambient, that drives gases into the soil, and when that pressure is reduced, that drives gases out of the soil by advection. And these processes happen daily, mostly due to pressure changes, but also due to ambient temperature changes. So the soil respires, really breathes in and out once a day. This is known as barometric pumping, and this technique is not barometric pumping friendly. So the third method is the CO2 traps, and the idea here is that you essentially put just a shallow receiver in the ground and connect to a trap that has a layer of sorbent. The sorbent captures CO2 as it leaves the ground, but recognizing that ambient air also has CO2, we put a second layer of sorbent that captures the ambient CO2 that is trying to get into the bottom layer. So as a result of this device, the bottom layer captures the CO2 coming out of the soil. The top layer keeps the ambient CO2 from interfering with a measurement from the bottom layer. And here we have different colors of CO2 because here we're suggesting that there's a difference between CO2 produced from from natural processes in soil, plants, and microbial activity, and the deep CO2 would come from the petroleum degradation. And both of these types of CO2 have a different isotopic signature that I will describe at depth later. So here we have an animation that illustrates how some of these processes happen in the soil. So here you have your source, and the source is generating this biogas, and the biogases are now moving in the soil, and ultimately they daylight. And when they get released into the atmosphere, then this sorbent captures it. So when these traps, after these traps get deployed, they get retrieved by site personnel, capped, and then shipped to the laboratory for analysis. And here, that's where we do the differentiation between the modern carbon and the old carbon. This is how they look in practice. This is just a shallow receiver pipe in the soil. This only intrudes in the soil about 2 inches. And then you deploy your trap, and the trap stays in the ground for about 2 weeks. It has no power nor moving parts. It's a field method, but the analysis is laboratory. So we always do carbon isotopic analysis. And these measure the time-integrated long-term flux. They account for diffusion and advection because the sorbent is a porous material that doesn't impede the flow of gases out of the soil. The disadvantage of this method is that it takes about 4 weeks after it's received in the lab to be analyzed and provide the carbon isotopic results. So after this brief introduction of the different techniques, I'm going to switch gears and I'm going to talk about some of the data that we have from some of the initial pilot studies that we started at CSU, Colorado State University. And we started with 3 former refineries, 2 active refineries, 1 rail yard. And we had in the order of about 100 sampling locations. We did multiple measurements at these locations. So in the end, we had about 200 measurements. And before I describe this data, I want to talk about the units. The traditional agronomic units for CO2 flux are micromoles of CO2 per meter squared per second. This is the raw measurement of CO2 flux. And if you make very few assumptions, if you assume that 1 mole of carbon being degraded in the contaminant turns out it becomes 1 mole of CO2. In other words, if you assume the stoichiometry of the reaction and you assume the density of the hydrocarbon, you can transform these agronomic units into units that are comparatively similar to what people use for remediation of petroleum, which is in the US, in imperial units, gallons per acre per year of petroleum biodegradation. And the second thing that you have to know is that the total CO2 flux is really the result of the natural CO2 flux and the CO2 flux resulting from the biodegradation of petroleum. In other words, you have to eliminate the interference from the natural CO2 flux. And there's a couple of ways of doing this that I will describe. In this case, this is a paper that we got published in Groundwater in 2014. And this is a map of a site that is close to a river. It is a former refinery. And the shaded area right here indicates where the petroleum contamination occurred. They did this with laser-induced fluorescence survey. And the locations here are where we measure the biodegradation of petroleum. We included 3 locations that were not contaminated. These are called background locations. And what we did is we background corrected the CO2 fluxes. And so if you take the average of the background CO2 flux and deduct that, subtract that from the total CO2 flux measurement, then you get the background corrected CO2 flux numbers. And then we have multiplied this time the stoichiometric factor that gives you the units of gallons per acre per year. So when we do that, you know, some of the fluxes are not any higher at the contaminated areas than in the background areas, but some are still in the order of 1,000 gallons per acre per year, or 2,000, or maybe in this location as high as 10,000 gallons per acre per year. In fact, we have a triplicate location here because we didn't believe the single number that we first obtained there. So something else that was done at this site, and it's in that paper, is that the highest temperature in the groundwater was measured, and it's plotted here spatially. So the lowest temperatures are about 14 degrees in groundwater upstream from the contamination. As the groundwater travels through the contaminant towards the river, then it starts picking up heat, and the temperature increases as much as 4 centigrade degree here. And when you plot these degradation rates, you see that these the highest degradation rates are correspond to the highest temperatures in the groundwater. The plot here shows a microcosm study in which some soil out of this ground was taken to the lab and incubated at different temperatures. It was incubated from 9 degrees all the way to 40 degrees. And what you see here is that the microbes seem to like it the highest at 30 degrees. And so, in other words, when you have highest temperatures in the ground, that speeds the reaction, and that might be causing these higher biodegradation rates. So I now will describe some of the use of carbon isotopes to refine these degradation rates. The main, so there's 3 main isotopes: C12, the most common one. There's C13 and C14. And in the case of C14, C14 is produced in the ambient air by the action of cosmic rays, but it's unstable. So all sources are completely depleted of C14, and modern sources have a stable ratio consistent with the amount of C14 in the atmosphere. The half-life of C14 is about 6,000 years. So by the time that organic carbon is the H of petroleum is completely depleted of C14. There's a little bit of an enrichment due to C13 because microbes use lighter isotopes. They prefer to use lighter isotopes. So what is left behind is enriched in some of the heavier isotopes, and the CO2 is has a lower amount of C13. Mostly this is a bit of academic information. We don't use that for our measurements, the C13. So mostly I'll be describing the C14. So the 2 alternatives to account for modern carbon processes is the C14 analysis, and you have the old carbon that has no 14, and that's called fossil fuel carbon. And the modern carbon, which is has a constant amount. And there's a way to use the C14 analysis to estimate the fractions of both modern and fossil fuel. There's an ASTM method for that, and we use that routinely in the traps. The second correction that exists is the background correction, in which you measure the total CO2 flux at an unimpacted location in the manner that I described for this particular case study that I showed, and you subtract that from the total CO2 flux. So you take a location that is not impacted and use that to estimate the natural CO2 production rate and deduct that from the total CO2 flux from contaminated locations. So first, I'll describe the basis for the C14 analysis. As I indicated before, there's an ASTM method for this. And the idea here is that you have a modern source that has an isotopic ratio of about 150 per mil. And that is characteristic of ambient concentrations. And on the other hand, you have a second source that is old and has no C14. And because these sources are known, if you mix them at a certain ratio, you get your environmental sample. In this case, if you have an environmental sample that has about half of the C14 than modern carbon, it indicates that half of that sample came from modern sources and half of it came from fossil fuel sources. And you can do the mass balance for any, really any amount of fossil fuel in an environmental sample. Here I did a study for 4 sites. We compared essentially the natural production of CO2 by both techniques. This shows you the CO2 flux, and we have 4 sites. And here for both sites we have what is known as a box and whisker plot. And the box and whisker plot is a way of characterizing a population by having the box is made of, the center of the box is the median, and then the extremes of the box are the 25 and 75 percentile. And then the whiskers of the plot are, it's a standard deviation. In some cases you have outliers which are indicated as asterisks. So a box and whiskers plot is just a way of characterizing a group of data. And here we have 2 groups of data. We have the modern carbon CO2 flux on the left, and on the right we have the background measurement. Of course we have that for 4 sites. So there were fewer locations for background for total flux, and we all had measurements of modern carbon for all locations measured. So here in the first case we have that the background location showed very similar CO2 production to that indicated by modern carbon production. So there was some consistency here. Here the second side, the same thing, but we see a couple of outliers of modern carbon in the second side. In the third side, there's a large difference between these. The background correction was producing a lot less CO2 than the contaminated locations. And the opposite was happened on the last site. The background location had much higher CO2 production rate than the contaminated locations. So this is the interference to the measurement, and this slide shows what the final result of the NSZD estimate is using both techniques. Again, box and whiskers plots, and you have in the first side you have similar order of magnitude using both techniques. However, the use of the background location resulted in larger variability here using the background correction. For the second side, there was a bit of an overlap of the ranges, but the results were relatively consistent. In the third and fourth side, however, there were large differences using both techniques. You get much larger variability using the background correction in both cases, and in some cases you get negative degradation rates. So the background correction assumes that the vegetation and modern CO2 generating processes are similar between impacted and impacted locations. And really what we have learned is that C14 analysis allows for location-specific measurement of the noise, the interference of modern CO2 produced, and therefore a better estimate of the fossil fuel-derived CO2 fluxes. And in all cases, the background correction introduces larger variability. This is a plot of CO2 production rates at an agricultural site for multiple years. So this is each line is for 1 year, and this was done for multiple years. And what this shows is that these natural CO2 production processes vary seasonally, but they also vary year by year because every year has a different weather, different precipitation, and ultimately that is really the noise. So the reason for the background correction being so variable is that the surfaces at petroleum contaminated locations look like this. You have some bare surfaces and you have surfaces that have different vegetation. So this background correction really is location specific. It's not site specific, it's location specific. So we think that the best data is to use the C14. It comes from the use of C14 analysis. In the case of the ranges that we obtained, this is a summary of those. This is the 4 sites that I showed before, and the average across all sites is 2,700 gallons per acre per year. The highest goes as much as 3 times that. And this highlights that the magnitude of these degradation rates is pretty significant. A measurement of 1,000 gallons per acre per year is not uncommon, and this highlights that natural source and depletion should be accounted for in management plans for petroleum contaminated sites. So in a few more minutes, I want to go over a few more things. How do you use the data? One of the first comments that we got from regulators is those measurements that you're getting are too high to be credible. So if you take a large number, let's say 1,000 gallons per acre per year, and you do the unit conversion, this is a straight unit conversion. There's no assumptions here other than units. 1,000 gallons per acre per year is equivalent to about 1 millimeter of free petroleum loss per year. So if you have a site that has, in the US they use inches, so half a foot, 6 inches, is about 15 centimeters. So if you have 15 centimeters of free petroleum at your site, your experiences losses that are lower than 1% per year. So the lesson is, even if you have a large degradation rate, you still can explain the longevity of the site for multiple decades. So how do you use the data? You can use the data to map contaminant sources. Of course, you can use the data to consider natural source and depletion as a remedy. It's not a remedy for all sites. It might be only a remedy for a low-risk site. And natural source and depletion can be used as a benchmark for active remedies, specifically hydraulic recovery and the performance of soil vapor extraction systems. This is a conceptual plot that shows that in the life of a remedy, the performance is variable. Initially, you get high performance. If you install extraction wells, you get a fair amount the first year. The second year you get a little less, and every next year you get a little less and less. You still get some, but cumulatively it's not changing things. And I call this the asymptotic performance of this curve. What is recoverable? That is a very important question. And it might depend on what the residual is. It's a site-specific metric, and as a reference, in the Bemidji site in the US, which is one of the most well-published sites, people found that about a third of the petroleum was not recoverable, and that's using the best science. So the specific values depend on many things: what type of remedy it is, what stage the remedy is in, but when the remedy is at late stages, typically you can get very small efficiencies, such as 100 gallons per acre per year. And at that point is when you should have this conversation about whether or not natural source and depletion is achieving more than the active remedy. So this summarizes the lessons learned. I want to leave some time for questions. I haven't checked if you have any questions. so far, but if you have any, just type them now or at the end, and we'll get to those. So the lessons learned, this is a plot of 4 different monitoring events at the contaminated site. These are background corrected losses. And this is a plot of the ambient temperatures throughout the year. And this is the spread of the numbers of the degradation rates estimated. And when it's hot, some locations are really showing a large production of CO2 and a large estimated degradation rate. Some other locations are low, but when the temperatures drop, the entire group shrinks. So microbes are sensitive to temperatures. So these NSZD processes are seasonally variable. The Veda zone natural source and depletion losses show higher estimates than groundwater-based losses. I didn't go into detail into that concept, but the idea is that the flux of electron acceptors from groundwater is limited by the solubility of these and groundwater transport. So because these processes proceed by methanogenesis, and methanogenesis does not require electron acceptors, external electron acceptors, methanogenesis seems to be proceeding at faster rates than the groundwater-based processes. So on one end, the processes are showing stronger in the Veda zone, but it's also a lot easier to measure things by these relatively new techniques in the Veda zone by measuring the CO2 fluxes at the ground surface. And so looking for these NSZD rates is a lot easier and offers a lot more return for your investment in the Veda zone. You know, what we have learned is that NSZD rates are higher than previously thought. There has been comparisons of different techniques, and the range of the magnitude, is similar between different techniques. There's also side-by-side comparisons in the lab that have been done, and these methods are shown to be consistent with each other. These NSZD rates are consistent with the performance of active remedies and with the longevity at the sites that is observed for multiple decades. I already covered this, so you know, I think the only thing that I want to stress out is that in all of these measurements, you need to make sure that you really are accounting for only the CO2 that is being produced from the biodegradation of petroleum. And the best data for that seems to come from C14 analysis. Natural source and depletion is coming of age. It's important at most sites, and quantification is the key to incorporate this into the management. And there's new guidance documents. This one from the API guidance document is available now. It includes the 3 techniques that I described. As well as the new ITRC LNAPL guidance document will come in a few more months, and it will be consistent with the API guidance document. So at this point, I will just describe that we have done measurements at about 80 different sites in the US, a few in Central America, many in Canada, Australia. NSZD in Australia is really a hot topic. And we have projects as well in Europe, in Spain, the UK, France, and Germany. And with that, you know, I'll open it to questions. If you have any questions, please type it, and we have a few minutes in which we could answer those questions. The first question here is if we can get a copy of this seminar. Yes, we'll. There's a version already posted on our website of a previous seminar that is very similar to this, and I have recorded this seminar, and it will be posted on the internet in the next few days.